Okay, I'm Jamie. I'm an undergrad at Illinois Tech. This title was kind of long, so don't read it. You can look at the first line and think cold start. Well, look at the first line and you can think like FunkX. The second line, you can think Docker sucks. And the third line, you can think unikernels are awesome. Okay, so I'm going to get started and I have a lot of stuff to explain. Cool. So first, let's talk about cold starts. So, there we go. Cool. There's a bit of a lag, sorry. So we start, why do we use containers? Dependency management. It's a really good abstraction for understanding what packages and devices you need to support for your application. This is a problem. Containers have poor performance or poor cold start times inside HPC systems. So this table is taken from the original FunkX paper. And you can see that you have like a cost of using a container in the order of seconds, okay? This is pretty good. This could work. You know, if you have an app that runs for minutes or days or weeks, then who cares? But if you have in a serverless context, we have a smaller application, this really matters. And it gets worse, right? So we see that in FunkX, we have many libraries, and some of these libraries touch many files. Okay, so this shows from left to right, most common libraries, and then number of files these libraries touch, right? So you can see something like TensorFlow, PyTorch, Pandas touching in the order of hundreds to thousands of files. And then you can also consider the fact that, you know, on an HPC system, you have a shared file system. So this shows the degradation of read performance of the same read file or the same read size, 200 megabytes, as you increase the number of files being read. A bit of context, this is on with many processes across many machines, right? So we start at hundreds of megabytes per second, and then we go to fractions of a megabyte per second if you're reading 10,000 files. So if you combine the past two slides, you get something like this, where you see and thanks a lot for this graph, you see that a few nodes, a few processes, find startup or find import time, right? But as you increase to many nodes with many processes importing TensorFlow, right? You know, consider that thousands of files and hundreds of nodes, and that shared file system performance, it can take up to 10 minutes. Right, and so we can see that we progress from a baseline of a few seconds to many minutes just on the input TensorFlow part, which is pretty impactful. So what are unikernels and how can they help? So just quickly, a unikernel is an operating system built for a singular application. So you can kind of think of it as, you know, your traditional system, you have your operating system and your kernel, and you support many libraries, many devices, and so you can support all of your applications. In a unikernel, we only support the specific libraries and devices that your application needs. So if your application doesn't need a GPU, then we don't supply a GPU device driver. And you know, this is a little trick that we OS people have done in the past few years to allow people to, or to convince people to allow us to make operating systems, is we put our funky operating systems on top of virtual machine managers. So we don't force people to change the OS of their system. So how do unikernels help? So first off, if we take in the fact that a unikernel only provides libraries and devices that your application needs, it's going to just be lightweight. And so outright, in this experiment, we compare the performance, the cold start time of booting into the Python interpreter on a unikernel on top of a lightweight hypervisor, and then a lightweight Linux distribution on top of Docker, and a lightweight Linux distribution on top of Firecracker, which is just a micro hypervisor, right? So outright, just because our unikernel is so lightweight, we can beat both of these. This isn't, you know, this doesn't consider your shared file system performance. This is just booting into the Python interpreter. And next, this is an experiment that we haven't done yet, but something we want to do in the future, combine the poor performance of a shared file system and the read pattern of a unikernel. You know, you combine all of your libraries and drivers into a singular image. And so TensorFlow, you know, which reads thousands of files, looks like this in a shared file system, TensorFlow inside of a UniKernel would have a read pattern like this, because all of the libraries, all of those files are in that singular file, the singular UniKernel image. So what's the big picture? So we kind of envision users treating unikernels like Docker containers. And there's a lot of work that goes into, building off that. So first, you need a build system where users could specify Python dependencies and get an image out. Next, you might want to build a virtual machine manager. So QEMU, KVM, and Firecracker work now, and they're great, but we might need better. And, building the operating system itself gives us the opportunity to tailor system calls towards the systems that we see. So if we notice that we want to coalesce reads that are done inside of the image, we can combine all those system calls because we're at the kernel level. We can collect all those system calls and do one big read to be even nicer to the shared file system. So a few things we want to do in the future. So make a unikernel that can support Python libraries. So the one I showed just boots the Python interpreter. It doesn't support TensorFlow or anything. So that's something I'd have to add. Measuring that, and then taking that unikernel and measuring its performance on a shared file system. Some medium-term future work is that the platform we use to build these unikernels is modular, so again, we can modify system calls. And then lastly, it would be interesting to modify the virtual machine manager to support snapshotting. So snapshotting allows you to have even like hot start. We can take all of the data from the page tables, the registers, and do kind of like a context switch and store all of that context inside the kernel image itself. So imagine you can start instead of having to boot your operating system, do a bunch of setup and then load into the Python interpreter, we boot the operating system and we're already in the Python interpreter. So that's the kind of performance you can see with snapshotting, and building a unikernel enables us to achieve that. So real quick, shout out to the homies that helped out. Kyle over there, he's a nice guy. He helped me turn this project kind of idea that was like bouncing around in my head into a cohesive story that made sense. Valerie helped me make stuff work because nothing worked. My advisor at Illinois Tech, Al Hill, he's an operating systems guy, so he would help me, make sense of all of the kernel stuff. Alex is another piece, or I guess now he's a professor at DePaul. He helped me set up a cluster. And then Ryan gave me the data set with common Python libraries. These are my references with, all the cool papers I read. And then in red, you can see where I, put what data from what slides. I'll take questions.
Talk about coalescing read calls.
Yeah.
And I'm curious how much you need from the application to know that. If it's blocking a read call before it gets you another read call, how do you coalesce those if the application doesn't move on?
So honestly, that was like kind of like something I threw out there. If the application needs the read to happen, like it's synchronous, I need to know that this has been, or sorry, I should have said coalescing writes. That's what I meant to say.
Okay.
So yeah, so my bad. If the write is synchronous and the application needs to know that this is on disk, then of course you can, you have to perform the write. But if it's just a asynchronous write, I just need to know if this happens at some point in time, then you can coalesce them. So I meant to say coalescing writes.
More detail, I'll ask you later. Anybody else?
This rocks. I'm unikernel pilled now. And like when you mentioned the future work, there's like, okay, how can we like do things like import Python libraries to make this more of like a Docker stand-inable thing? And I'm curious, for that future work, how much of that it feels to you like, oh, hard, operating systems, research style stuff, and how much of it is like, no, we have the core things, and we just need to make like nice developer tools such that people could drop this in where they're currently dropping in containers.
Yeah, absolutely. So there's 2 parts to it. I think like in the immediate future term, 80% of the work is going to be that hard. We need to port libraries. So something I didn't mention for a good reason is that this supports like a Musel is like a minimal C library. So it's like a analogous to glibc, right? So Musel is a minimal C library, and that's what this uses. And that works with Python, but other applications might need more complex C libraries. And so that is something that we'd have to like look into porting. A lot of this would be just porting and porting applications. But I believe that once we have like a minimum set of libraries, once you have glibc, then you open up a million applications. If you start supporting, I don't know, TensorFlow, because now you have glibc building off of that, you can probably support TensorFlow. Now you have a million more applications that you can support. And so, yeah, in the immediate term, there is some porting work, but I think that opens up more doors. Then, yeah.
Thank you.